Hi there. Behind me you can see an example of a particle system where when the particles get close together they draw a line to one another. You can find this example on the p5.js website or one similar to the one that I'm showing you there. If you click on the examples, let's check that out. Click on the examples at the p5.js website. In the simulate section, you'll find an example at the bottom called particles. If you click on it, you'll see an example of what I was showing you there. In the example from the p5.js website, those particles have a set vector or heading, and they have a set speed that they're going. And when they go off of one edge of the screen, they come back on the other side. And when they get close enough to one another, they draw a very thin line, and that line just disappears or it appears. And it doesn't really change too much other than the length when they get closer or further away. This is done in a class, and you can see here it's kind of hefty. We're going to do something completely different. Well, not completely different, but the movement isn't going to be this set vector with a set speed. We're going to move instead through linear interpolation, and you can find an example of that. Just click on the examples, and if you go down to, I think it's math, and click on linear interpolation, you'll see an example of the kind of movement that I'm going to be trying to achieve. So we can think about the big circle as being our object, and the mouse as being the target. So what if we, every once in a while, pick a new location, and then move to it, pick a new location, move to it, new location, move to it. Just do that for every one of the particles. So that's how our movement is going to function. Now, what's linear interpolation? What's interpolation in general, whether it's linear or not? So I'll help you with that. I have diagrams. So here's a diagram that kind of shows what's going on when you're taking a set of one things and you're trying to fit it into a set of other things, and they're not the same size. The first thing you have to do is figure out what's the ratio of things. In this example, the ratio is 1/2. There's 5 of one thing and 10 of another. And it doesn't really matter what you're trying to fit them into, whether you're trying to make 5 things in this example. You can see the values there, how they map out. What if we're trying to map those to 10 things? Well, we're still using the same values, we just have more of them. So it's kind of a really highly generalized example of how linear interpolation is interpolation is working. So in linear interpolation, we're doing this progression to a smaller or a larger value each time we go to the next step. So if we're moving through this range of values, in linear interpolation, your next set of values is going to be slightly different. So it's not fixed like it is here. It's going to be less. It's going to be diminished by a certain amount. And we can set that in the function that does linear interpolation. So back in the 80s when I was doing this in BASIC, I would have to do this with a separate module. There was no keyword that you could use that would do it for you. You'd have to perform all these operations yourself. Blessed is the JavaScript library that you could just call this keyword and perform this operation without having to even know any of this. But this kind of helps you understand where these operations are coming from and how they can be used in lots of different ways. So in the example that I'm going to show you today, we're using linear interpolation, the lerp function right here, and we're using that to get this movement from where the particle is to where it's going to go. And it's going to do that in like this slowing down motion. We're also using map to get some action with the stroke weight and the stroke's appearance. So this is kind of a short program, but it's pretty powerful, and it's going to leave you with a function that you can use for all sorts of things, because linear movement through linear interpolation is a pretty cool way to move. You have Brownian motion, you have Lave flight, or Levi flight and Perlin noise. Well, this is just one more tool in that toolbox of movements that you have. To get started on this program, we're going to need a new sketch. So let's do a new sketch here. We're going to set the canvas to the available width and height. In Draw, we're going to clear the screen completely each cycle. And in Setup, just in case we want to change things in Draw, we're going to start out with the clean screen. So say we want to drop this down to 25 and we want to leave trails. Well, we want the screen to start out nice and fresh. So that's what these two background statements are doing. In our global space up here in the very top, we need to declare an array. We're going to set it to how these things are moving. So I'm going to use the word heading, and I'm going to tell p5.js create a new array, a blank array for this variable. How many particles are we going to have in this system? Well, we need a variable to hold that, and we also need a variable to let us to let the program know what range are we working with. When particles get so close together, they're going to perform this action. We need to know what that so close together is. So that's what that R is going to do. In Setup, we need a loop in order to instantiate all the objects and put them in this array that we created in our global space. So let's create that loop. Inside the loop, we're going to use that variable that we created up there called heading. We're going to use the dot syntax and the push keyword. Inside push, we're going to use the new declaration, and we're going to create a new instance of this object that we're going to create, this function called mover. Now mover needs some information. It needs to know how frequently are we going to be picking a new spot to move to. In other words, are we going to give our object dot time to get to this location and then maybe hang out a little bit and then go to the new location, or are we going to have it bouncing all over the place? That's the characteristics that you can get to come out of this value here. I want it to go to the spot and hang out a little bit. So I'm going to make this percentage chance of picking a new spot at 1/2 of 1%. So there's a 1/2 of 1% chance that it's going to pick a new spot each frame. That's pretty low, but it's going to be frequent enough that I think it's going to be kind of dynamic. Then in the lerp function, it needs to know how much are we decrementing this ratio each time we factor the lerp, the distance. So a larger distance is going to be more in ratio, and a smaller distance is going to be in smaller ratio. To tell the program what that value is going to be, we're going to send that into the function, and it's going to be a pretty small value, so it's not going to zip there really fast, and it's going to slow down before it gets to it, and it's going to do that by this rate here. I'm not sure if that makes sense, but just follow me for now. Try to follow me for now. That's everything for the setup. Inside Draw, let's give ourselves some room here. Inside Draw, we need two loops. We're going to start with the first one, and we're going to run that part of it, and then we'll put the other loop in there that's going to check the distances, and then we'll run that. So easy thing first, let's make a loop that goes through all of the elements in our array. I could use the variable POPU here, just like I did up in Setup. It would make no difference. But I just like to maintain that consistency of, if I'm using a loop through arrays in Draw, I'm always going to use the length of that array, instead of just using the value of whatever population or densities or whatever. Inside our loop, we need to look at our object, whichever one is in the array. So that's that heading variable, and then the loop is our index value, so we're going to put that inside there for whatever element it is. Now for that object that's in this variable heading.i, it contains a function object. And inside that function there's a method that we haven't made yet, but we will, and it's called update. So we're going to use a dot syntax. We're going to put update, and I'm not expecting to pass any variables into update. I think we have all the information we need. So there's no values going into the parameters here. So what that's going to do is when it goes into the method of the function, the method called update, it's going to do some stuff to some variables that we're going to make up later on, .x and .y. So I can use those now. They've moved around, they've done what they needed to do. Now I can get the return of those values. I don't want to have to deal with all of this. This is a mouthful. So to make things easier, I'm going to use some local variables and assign it to the return for the x, the .x, and the .y that I expect to have in this function. Now, it's not there. I'm just assuming that at some point I'm going to put it there. This could be anything. This could be sneeze. This could be yellow. It could be anything I want it to be, just as long as I understand that these are the values that are for the location of this object. And the standard is using x and y. So once I have my shorthand for those, I can make my particle that's going to be moving around. I want its stroke weight to be pretty big because I'm going to draw a point instead of ellipse. It's going to save us a little bit of processing. Let's make it white, or no, yellow. Let's make it yellow. Full intensity. And then we'll just draw a point at that xh and yh value. So this is our object's location. Okay, if I ran this right now, it wouldn't work because there's no function associated with what we've instantiated and with what we're using in draw. So let's create that function now. We called it mover when we instantiated it, and we want to maintain that consistency. And we also passed some values into it, so we need some variables to accept those values. We're going to do r for the rate that the location changes, and s for the speed that it moves to that location. So inside mover, we need some values to start with. So when we instantiate this object, this is the values that it's going to start with. This is important later on because you can play around with how the state begins, and it kind of changes things initially. And maybe I'll show you that here later on once we get this made. But we do need a location. So each particle is going to start out with a random location in the canvas, and it's going to have a random spot that it's going to head to when it moves. And we're going to make that XL and YL. And then we need an instance variable for our rate, which is the R that comes in through when we pass it in, and the speed, which is S that we've passed in there. I think that's all we need for when we instantiate. Now we can do the method, which is a function update. We've named update. Well, that zero messed it all up. Okay. In update, pretty simple. The first thing we want to do is check and see if we need to move our location. We're going to do that by taking a random number between 0 and 1 and checking to see if it's less than our instance value, this.rate. If it is, if this condition is true, then we're going to change the location for x and the location for y that this object is moving to. Whether we've picked a new location or not, this object has a place to go to, whether it's its old position or its current, or it's just picked a new position and now it's going to go there. In either case, we need to move it, and that's what we're going to do here. So we need to move for x and we need to move for y. We're going to use the function lerp, and inside lerp it has 3 arguments that we have to give it some value for. So the first argument is going to be our location, where we're at. The second one is going to be where we want to go. And the third one is going to be how fast are we going to get there. So if you just remember that kind of thing there, where are we at? Where do we want to go? And how fast do we want to get there? So that's what lerp does. So right now we should have all the information that we need to make this thing move around the screen, to make a single object, or as many objects as we want, 25 in this case, move around the screen. So let's see if that's happening. And it is. Now you can see when the program first starts, they're all moving to their initial location. But then as the program's running, they get to those locations. Some of them do, some of them don't. And then they hang out for a little while, and then they move to their next location. So the behavior has changed. Initially, they're all moving. Now, some of them are stopped, some of them are moving. And when they first started out, they were just going to random positions in the screen. But what if when we instantiate it, instead of them going to random positions, they all move to the center? So we're going to make the initial location for our width be the center width and the center height for the Y. So these are going to be positioned randomly all over the screen, and they're going to be moving toward the center because that's where their initial location is at. So let's watch that run and see what happens. And you can see they're all moving toward the center until or unless they have a new location to go to. So there you go. Now they're moving around. The next thing we want to do is check and see, are they close to one another? And if they are, let's do something about it. So inside draw, we have our loop that's moving through each one of our objects. Now we need another loop that compares that the object that we're on with all the other objects that there are in the array. Okay, I'm using II, probably not the smartest way to do it, because there's a chance that I could forget to put an I here and an I there, and then the program's not going to work, and it's going to take me 20 minutes to figure out what's happened. That happened today. So if you do that this way, just remember to put 2 I's in there. I think now that I've made a big deal out of it in my mind, I'm going to be sure to double check it. You might want to use J, but whatever variable you use, just keep in mind that I is where we're at, the object that we're actually on, and J, or 2 I's in this case, is any of the other objects that we may be near that we're going through. So inside this loop, we want to do some things that make life easier. The very first thing is we're going to do the same thing with our object to begin with up here. We're going to do that with our target. So we're going to take the same array, except for the element value is going to be different. It's going to be that double I. And we're going to look at the X of that one and the Y of that one. And we're going to compare it to the one that we're actually on. And we can do that easily now. Since we have some easy variables, now we can look at the distance between our object and then all the other objects. So our object is xh, yh, and all the other objects is xht and yht. That's going to return a value between 0 if they're on top of one another, or a positive number that's equal to whatever distance they are away. It doesn't matter if they're to the left or the right. If those values are negatives or positives, they're always returned positive. Inside a condition statement, when we want to check the distance and compare it to our range, inside what distance do we want things to happen? And we only want that to happen if we're not looking at ourselves. So if the object is looking at itself, it's going to skip over it. But if it's looking at any other object, it's going to see if it's close enough, and if it is, it's going to perform whatever's inside this condition. The things that we want to do inside of it is we want to affect the stroke. So when it's close together, I want the stroke, the line between them, I want that stroke weight to be large. I want it to be a thick line, like a rubber band that's relaxed. And then as they move apart, that theoretical rubber band gets stretched and the line or the thickness should get thinner. So when it's further away, it has a thinner line, and when it's closer, it has a thicker line. And I'm going to interpolate that so that it's relative. And to do that, we're going to set a local variable, s, sw for stroke weight. We're going to use the map function, and inside the map function, we're going to use the argument d, which is our distance, and it can be a value between 0, which is right on top of the object, and r, which is the minimum value that this argument is true. So if it's right on top of it, I want it to be its maximum thickness, so 20 points stroke weight. And if it's as far away as it can be, I want it to be its thinnest, so 1 point stroke weight. Once I have my stroke weight, now I want to do something with the fade. If it's stretched, I want it to be more translucent, and if it's thick, if it's close, I want it to be more higher opacity. So I'm going to use SF for the fade, and we're going to map that stroke weight. So if it's a small stroke weight, it's going to be full opacity, and if it's a small stroke weight, it's going to be its lowest opacity. Well, its highest stroke weight can be 20, and its lowest stroke weight can be 1, and we want its highest opacity to be 255, and its lowest, we still want to be able to see it, so we're going to put that at 50. So now we have our stroke weight and our color, so to speak. We can put those attributes in here. In our stroke weight, we're going to use the SW, and then in our stroke, we're going to use SF for the alpha part of that. Now we can draw our line between our object's location and all the other objects' locations. Just like that. So if we did this correctly, I'm hoping we did, this should work. And it does. You can see as the points get closer together, they make a narrow line, and it gets thicker as they get on top of one another. And then they hang out. So if they're kind of close to one another hanging out, that line may stay there, static. And then it'll move and go wherever it needs to go. If you like this video, thumbs up. If you want to see more content like this, hit subscribe, hit the bell to be notified. And I guess that's it for this one. Let me know what you think in a comment. Until next time, as always, thanks for watching and take care.